So welcome to the lecture on function approximation. So in an actual application, the data scientist needs to decide which model to use. So linear perceptron, fixed basis functions, neural networks, kernels, and so on. And then the problem has to be solved with the actual data actually available. And in the lecture on model selection, we'll discuss how we find out which is the best model in a systematic way. But what can theory tell us about these issues? So in this lecture we talk about practical issues. So for example, why are deep neural networks so successful? So in this lecture we will be a bit informal, since formal treatments require advanced mathematical frameworks and are beyond the scope of this lecture, but I think the main points can be understood. So let's first consider the set of all possible functions. All functions can be realized by small n to the power m linearly independent basis functions with n discretization steps for each of the m input dimensions. So we consider x not to go from infinite to minus infinite to infinite, but let's say from 0 to 1 or some other bounded set, and we discretize this into small n steps. And since we have m inputs, we need n to the power of m resources. So you can think of every bin, so every sort of discretized inputs can define a basis functions or use another basis. But to be able to model all possible functions, you need n to the power m, not because they're n to the power m bits, for example. And if we are happy with precision of k discretization steps for the function, so for the output, we can realize k to the n to the power of m functions, which leads to the entropy as a log of that number, small n to the power of m log k. Or another way of looking at this, if every bin, so every possible input, has to be represented by precision of k, so the functional value with k steps, then we need log k bits for each bin, and there are n to the power of m bins, so we end up with n to the power of m log k. So it's interesting, if you look at this formula, the log k is not really so dramatic. Even for a nice precision, log k is relatively small. But the number of inputs, n, and the dimension m is what kills you. So the factor n to the power of m. And this would be an astronomical number for a reasonable number of inputs m. First of all, Mother Nature is kind to us and typically does not realize all possible functions. So, for example, if you think of image classification as a map from images to maybe a class label, a cat or dog or whatever, a person on the image, then this dependency from input to class label is not arbitrarily complex. So there are some smaller sets of functions which are realized by nature, and the art in machine learning is really to use the right functions for your models for the problems at hand. So so this is maybe the situation. This is this huge space of all possible functions, and a number we can derive would be this n to the power of m times log k, and this is the these are the functions which are actually realized by nature for a certain problem. So this T, this calligraphic T, is the set of target functions, and they are smaller than all possible functions. And this is, you also get a feeling that this is sometimes theoretically difficult to analyze, which is why one reason why people pretty late went into the approximation of high-dimensional functions. So, for example, maybe these functions have some smoothness characteristics or some other thing. But it's difficult to characterize, and that's one reason why deep learning is so powerful, because it seems to capture that class of functions quite well. But in essence, the target functions assume a tiny space in the space of all possible functions. So it's much, much smaller than this number. And if this would not be true, machine learning would essentially be impossible. And people thought it was impossible. So even in my times, people in approximation theory and so on, they did one-dimensional functions or maybe two-dimensional, because images were important, but they really shied away from higher dimensions. And only machine learning really showed that this can be done. So we have to come up with some, so this was the target functions. So these are the two functions generated by nature. And now we are considering a model class M. So that's, okay, I'll show in the next picture in a second. So, and often we assume the model class is defined by some function with some free parameters. Now we learned about basis functions, and these W's from the basis functions would be the free parameters, and the model class would be maybe defined by a fixed set of basis functions. And we are interested, one thing we are interested in is the worst case difference between the true function, this is the true function without the true, yeah, and the best one out of our class. So this is the W-opt. And if we choose as our model class fixed basis functions with M phi basis functions, so which is an incomplete basis, obviously, then this astronomical number reduced to M phi log k. So that's much nicer. So if we can control the number of basis functions, we are in good space. So let's look at this picture. So this is now already the smallest set of functions generated by nature. Difficult to characterize, but it's smaller than the set of all possible functions. And the green one is the set of functions which we can model with our model class. For example, fixed basis functions. Yeah. And this is sort of the worst case. So this, if nature decides to realize this function, this is the best one we can get. So this is sort of the if you want to look at it as a distance, then it would be the square of the bias squared. So this is a positive number. It's a distance, and we will learn later how to look at this quantity in reality. Or if we are lucky, then the model we are looking for can be realized by one of the functions out of our model class, and then the approximation error here would be 0. And we want to have a big overlap. We want this region to be large, because this is wasteful. We can model functions which never occur in nature. This would not be a nice thing. And so we want to have a small epsilon. But we also want to have a small space here in the green region. And this is probably what we are typically having. So our model class is sort of contained in the class of all interesting functions. Here we see the worst case, sort of the largest distance between the worst case function from the target class and the best fit from the model class. And this space is maybe defined by the number of basis functions times log k. and and even m phi could be too large, so we have to get a way to get m phi smaller. Then, in addition to approximation error, there are also statistical errors. So even if we know the best, I mean, we can model the target function, but we have to estimate the function or the parameter, the w, based on our finite data set. If we would have infinite number of data, then we probably could say we find the best function out of the model class to fit the target. But since we have a finite number to estimate these w's, we will have some errors. For example, a typical quantity is a number of parameters divided by n. So this error goes up when we have more parameters, and it goes down when we have more parameters, more data points. And we will discuss this also in more detail later. So in this case, for example, with so red one means with our best estimate with a finite number of data. There will be a difference between the best possible function, so this green one, and the one we are currently estimating. Or here, even if the true function can be realized, we have an error because we don't know the parameters of the best model. We just know we can just estimate it based on data. No? And if we look at this also as a distance, so in many cases we can just add the square of these two numbers. So epsilon square plus this distance square is something we want to make small. No? And there are often compromises. We can make this variance small, but then we introduce more bias, or we make bias small and then we add more variance. We will see that later. That's the so-called bias variance dilemma or trade-off. And then there are some other issues. Computational complexity, memory complexity. We will not discuss this too much, but for example, how long does it take to train the model? And for systems with fixed basis functions, this is typically on the order of a number of parameters to the power of 3. So we have this cubic dependency. Then how expensive is the prediction? That can be important if you need to make very quickly a prediction, for example, in advertisement placement or search engine results. You don't have much time. In other application, this doesn't matter too much. And then there's memory complexity. So how much memory do I use in training and also in prediction? So how do we define the distance between functions? So let's consider two functions, f and g. And so what are we doing here? We're taking the difference between the functional values at x, and we take the square of this difference, and then we integrate over all possible x. And since we don't want to deal with infinity, so we restrict this distance to a unit ball. So consider a region around 0 with maximum distance from 0. That would be a ball in n dimensions. Now, so this is simply the squared Euclidean distance applied to two functions. And then the approximation error is this distance with a ball, and the maximum approximation error would be the largest distance between the best function out of our model class and the worst function out of the target class. And the statistical error would be more the expectation of the distance of the optimal one we can get and the one we can estimate from data. And we will talk about this term more in the future. Another definition is to introduce a probability distribution, P of x. So you can think of this maybe as a Gaussian centered at 0. And so we don't just integrate over the ball, we multiply it by the probability that this x occurs. So if you have a uniform distribution on the unit ball, then the two definitions are identical. And this can be an important difference, because P of x might be really odd-shaped. We saw this example with the manifold. So if the data is on a manifold in training and in test, then the relevant P of x can be very non-trivial. And this will become important again when we talk about learning with manifolds. So in the first analysis, remember we had maybe n or 10 basis functions per dimension, and then in 2 dimensions with a tensor product we get 100, and it goes up exponentially. So we seem to run into this problem that the number of basis function sort of increases exponentially with the dimension, where a is the number of sort of basis functions per dimension. Yeah, this is the curse of dimensionality. Here's something for maybe a little bit advanced. So for systems with fixed basis functions, the VC dimension, which is some key concept in statistical learning theory, and we will discuss it briefly later on, is the number of parameters, which is the number of basis function in this case. So it is proportional to our definition of entropy. So let's give you some hint of what this VC dimension is. So proportional to the number of bits required. If we have exactly as many data points as basis functions, the design matrix phi transpose phi, so it's this matrix, phi is the design matrix. So this is a square matrix and might be invertible. And we might get a perfect, so if they are linearly independent, then it's invertible. So we get a perfect fit for any training labels. And according to the VC theory, generalization can only start when we have more data points. Which of course is not true in reality, because we can use some prior knowledge to restrict this even further. But this is what comes out of the simplest form of VC theory, where this term has a little bit abstract definition. It is the cardinality of the largest set of points that can be shattered by the model. So where any assignment of targets can be perfectly fit, and as we just discussed, in this case it's obviously the number of training data points. In other classes like neural networks, the definition is more complicated. But this is just a preview on VC dimension. So let's continue with our discussion. So so far we did not discuss the approximation error, so one can derive the following equation. So epsilon, so the error we are willing to tolerate, is on the order of 1 divided by a to m. So a is sort of the number of basis functions per dimension, and m is something like a smoothness measure. No? So of the target class. No? So if the functions are smooth, so we would have a large m, then a to the power of m is a large number, and 1 over that is a small number, so epsilon would be small. If we have a very unsmooth function, m is small, a to the m is small, and epsilon goes up. So this can be derived. I didn't discuss how this is derived. Then we have another equation. The number of basis function is on the order of a to the power of m. And if we plug this result, so if we solve this for a and plug it into this equation, we get that the number of basis functions required is on the order of 1 divided by epsilon to the power of m divided by m. So, and this result can, for example, be found in this paper by Tommaso Poggio. So just to give you a feel, so if epsilon is 0.1, then this equation becomes 10 to the power of m divided by m. So the number of required basis functions goes up exponentially with m, but if small m is large, then this might not be so bad as before. So it's as we now will discuss, it really ends up to be this term here, the number of dimensions divided by the smoothness. And we distinguish different cases. So case 1 is the so-called curse of dimensionality. So if m is large, the number of input dimensions is large and m is small, so we don't have very smooth functions. Then m divided by m is a large number, it's in the exponent, and m phi becomes unrealistically large. Yeah, this is called the Bellman's curse of dimensionality, who first formulated this issue. As we will see later, it's not completely hopeless, but first, let's say we have this really bad message. So this is our example. So maybe the input dimension is really 20-dimensional, and we forget about that this has some regularity, so this just indicates it's a complicated function. Then we actually have this curse of dimensionality. But not every problem is like that. Case 2 I call the blessing of dimensionality. So if m is small, so the input dimension is small, but m is small as well, so m is not very boring, it's a complicated function, but the input dimension is small. So the target function can be complex, but the dimensionality is small. Then m divided by m might still be acceptable. And this is really the case which we discussed when we said we need to introduce basis functions to model the function. Because if we introduce enough basis functions, any function can be modeled quite well. And this is what I call the blessing of dimensionality, because the mapping from input to the mapping to the space of basis function increases the dimension, so it seems like a bad thing, but it also makes everything more linear, and so we can model this class of function, so a small number of inputs but high complexity, by introducing basis functions. So as an example, if you only have one input, so m equals 1, a Fourier basis function, so a is the number a, would form a complete basis even. So if the dimensionality is small, they can tolerate a lot of complexity in the function. So this would be case 2, okay, blessing of dimensionality. So here we assume we only have these two dimensions, x1 and x2, and it still have a complicated function, but with basis functions we can model that. In the example before, it looks very similar, but we assumed we really had 20 dimensions and we only looked at 2 dimensions, so I could cut through these functions base. Then m can be large if m is large. So if we have many dimensions but the function is relatively boring, this can also work. For example, when we discussed about ad placement or search engine classification or search engine ranking, then the number of inputs are sometimes 10,000 or more, and this can still be modeled by very simple linear systems, because the complexity is so small, because every input makes a small contribution essentially. And case 4, of course, is trivial or simple. If you have a small m, small number of inputs, large smoothness, then of course anything more or less works. So this is this case. So maybe 2 dimensions and even a smooth function, then almost any method performs quite well. So let's look back at case 1, which was the curse of dimensionality, and that's a critical one. But fortunately, even case 1 is not as hopeless as it first appears, since in reality classes are more restricted. And we discussed 3 cases. So the target class might have high frequency components, might be complex, but only locally. And the even sparser solution might be feasible. The second case is that the input data is restricted to a low-dimensional manifold. So P of x maybe it has some strange shape, but it's low-dimensional. And 1c is the target functions are composable. So this is discussed in the lecture on deep learning. So 1a is sparse basis. And this is something a neural network can exploit quite well. So we have a large M, so many inputs, and small m, so complex functions. So m phi would be large. But in fact, only a small subset of these m phi's have non-zero weights. Because maybe high complexity is only present in a restricted region in input space. And the number of hidden units with non-zero weights, or h, might even be independent of the number of inputs. And this, as we will see later in more detail, is a feature which neural networks can exploit. So you define a neural network maybe with h hidden units, and in neural networks you adapt internal parameters of the neurons, of the basis functions if you want, such that sort of they search around and find the best subset considering of h hidden units out of the possible m phi ones. So you can get away with a much smaller number of hidden units without necessarily sacrificing complexity, because the complex behavior of a function is typically quite local. And this is, some people argue, would be the key to understanding the success of neural networks. And we will talk about a theory of Andrew Barron, which makes this more concrete. So here would be an example. It is a complex function, but for example, the pattern only goes in one direction. In the other direction, it's quite boring. And this can be exploited, for example, by neural networks. Yeah, so far we didn't look or didn't assume any particular input data distribution. P of x might be uniformly distributed within the unit ball. But in case B, 1b, P of x is restricted to a subspace of a small dimension, much smaller than m. So although the data, if you look at every input separately, it is in this high dimensional space, but maybe it only occupies a very small part of that space. So instead of, let's say in the last case, the question was, now, so it's more mh, which might be much smaller than m, so the dimensionality of the manifold, which we call mh. And in this case, we can maybe replace m divided by mh divided by m. And since mh, so the number of, the dimensionality of the submanifold is much smaller than the number of inputs, we get maybe a much better behavior. And some models like neural networks and deep neural networks exploit quite efficiently when the data is on a low-dimensional manifold. In some approaches perform a pre-processing to find this manifold, like PCA or ICA, but a neural network sort of does that implicitly by itself. So this would be maybe a linear manifold, so this would indicate the high-dimensional space, and the function is quite complex, but the data is really only on this one-dimensional linear submanifold manifold, and maybe if you go in this direction, the function is quite complex, but it's complex in a small space. No? So, and this can be exploited. Or maybe this reminds you more of this image of our manifold. No? So this would be a nonlinear manifold. Data is only here, and if you go along this line, it looks quite complex. But you can forget, maybe ignore the high dimensionality in which this manifold is embedded. So why would nature generate data on a manifold? So let's see, I have some pictures here. Maybe I show the pictures first. So maybe the way nature generates images or something is really by starting from some low dimensions and then generating a high dimensional image of these low dimensions. No? So this could be maybe whatever 200 by 200 pictures image, and this is maybe some low dimensional space from which nature generates these images. Now and then, since it starts, let's say, with 2 dimensions, also the data in this high dimensional space would really live on this 2-dimensional manifold. No? And then the inputs have these characteristics that the data appears to be on this manifold. Of course, you might have a problem if in test this is not true anymore, and maybe we have a 3rd dimension which contributes to the images, and then in testing suddenly the data is not on the same manifold, and this leads to these adversarial problems you might have found in the newspaper or on the web, that for data which didn't occur, data which are very similar to the data which occur training data, the performance might get much worse. No? And we had this example before, no? Just to illustrate, this was the 1-dimensional space, no? Very boring, 1-dimensional, but if you project it into this 2-dimensional space, the data suddenly is located at this odd-looking manifold. No? And this can be exploited because this remains to be a 1-dimensional problem, although it is in this high-dimensional, embedded in this high-dimensional space. And some methods can exploit that. No? So in that case, maybe we can replace this m phi and don't have to use the m anymore. So, and these adversarial examples here, it's a little bit more formal. So maybe in the training, we get data from P of x, and the worst case looks quite reasonable. But if you then look at the whole ball, so also data which might not lie on P of x, so this is sort of one of these strange manifolds, and then suddenly we get maybe a large performance problem here. You might have seen these examples in autonomous driving, where you have a stop sign, and normally the vision system has no problem recognizing the stop sign, and then people manipulate this stop sign in some way. People would still have no problem recognizing it as a stop sign, but the vision system decides it's something completely different. So, in conclusion, basis functions perform a nonlinear transformation from input space to basis function space. To avoid the curse of dimensionality, this factor is important. So the number of dimensions, or the number of real dimensions, divided by smoothness. So smoothness is good, makes life simple. Small dimensions are also good, makes life simple. Null networks are effective when the basis is sparse. So this was our case 1a. Or when the data is on the manifold, 1b. Yeah, so I want to end with some table here, which discusses different approaches, and maybe some of them will be, introduced later and might be more clearer in later lectures. So, so the first case, remember, was a curse of dimensionality. Large M but low smoothness. So linear systems don't work because we need high complexity. Neighborhood methods don't work, like nearest neighbor methods. Fixed basis functions don't work. Null networks don't work. Deep null networks don't work. Kernels don't work. So this is really a curse because nothing works. But fortunately, nature is more kind to us. So the blessing of dimensionality was when the dimensionality was small, but the smoothness was also small. So linear systems don't work because it's a complex function. Neighborhood systems might work. Fixed basis functions work. Now we transform it into a basis function space. Null networks work. Deep null networks work, and kernels work. So everything works except for the linear model, because obviously we're saying the function is complicated. The third case was that the function is smooth, so everything works except for neighborhood methods might have some problems already. And the simple one, finally everything works. So that's the low dimensions and smooth function. Now, if we have sparse basis functions, now we need a method to find this subset of basis functions which are really relevant. Linear methods cannot do it, neighborhood methods cannot do it, fixed basis functions cannot do it, null networks can do it, as we discussed, deep null networks can also do it. Kernels cannot really do it. 1b was the data is on a manifold. Linear methods cannot exploit it. Neighborhood methods cannot really exploit it unless you do some pre-processing, same as fixed basis functions. But null networks work very well, deep null networks work very well, and also kernels work very well. And the last class is a class of composable models. So that will be in discussion of deep neural networks. So no methods can really exploit it except for deep neural networks. And that's supposed to be the reason why deep neural networks work so well, because they reflect functions which have this composable structure and which occur in many applications in nature. Okay, thank you very much.